I want to start today with a headache. Not a literal one, thankfully, but a computational one. A problem that drives computer scientists just completely up the wall.
I have a feeling I know where you're going with this.
Okay, so imagine I say to you, I just made a huge investment in stock.
Right.
As a human, your brain is instantly, subconsciously even, just waiting for the rest of that sentence. You need to figure out what I mean.
Right. Because stock is, it's one of those nightmare words. Are we talking about Wall Street? A
Right.
soup kitchen?
Or a farm? Or we're looking at cattle?
Exactly.
And then if I say the market is bullish, your brain it snaps into place. You know it's finance. You don't even have to think about it.
Right.
But for a computer,
Oh, it's so hard.
that process of figuring out which definition fits, what's called word sense disambiguation, is incredibly difficult. It's this wall that, AI has been banging its head against for decades.
It really is. It's one of the oldest, dustiest, most just frustrating problems in natural language processing. How do you teach a machine context?
And usually the answer is just more data.
Mm-hmm.
But today we're doing a deep dive into a paper that suggests, maybe we've been going about this all wrong. That we've been trying to solve this with one hand tied behind our back.
Or maybe with one eye closed.
Yeah, that's a better way to put it. We're looking at research from Swinburne University of Technology, a 2011 paper by Chungfeng Hu and Chengfei Liu, and their argument is, well, it's pretty radical in its simplicity. They basically just said, why are we trying to teach computers to define words in total isolation? Why don't we let them read the story?
It sounds so obvious when you put it like that, doesn't it?
It really does.
But you have to understand the history here. Computing linguistics was very siloed. You had the people working on, what does this word mean? That's a disambiguation crowd.
Right.
And then you had totally separate people in another building practically working on, who is this pronoun talking about?
And the two never met.
Never. They were strangers.
So the mission for this deep dive is to see what happens when those two worlds finally collide. We're going to look at how these researchers tried to merge word sense disambiguation with something called coreference resolution to finally give computers a sense of, the bigger picture.
It's about moving from just processing text to actually understanding it.
So let's start with the status quo. Before this paper, how would a computer normally try to figure out if bank meant a river or money? What was the procedure?
Well, the standard method, and frankly it's still used in simpler systems, is what we call the fixed window approach, or sometimes you'll hear a sliding window.
Sounds like a fast food drive-through.
A little bit. So imagine you're the computer, you're reading a sentence, you hit a tricky word. To figure out its meaning, the algorithm gets to look at, say, 5 words to the left.
And 5 to the right.
And that's it. That's your window.
Just the immediate neighbors, that's all?
Usually, yes. The assumption is that the clue must be right next to the word. But that feels so limiting. When I'm reading a mystery novel, the clue for what's on page 10 might have been planted way back on page 2.
Exactly. A fixed window is, you're essentially giving the computer tunnel vision. If it sees the man went to the bank, it can probably figure that out. Money or deposit might be nearby.
Right.
But if the sentence is just, he went to the bank, and the clue that he is a Wall Street broker was 3 sentences ago, the window misses it completely.
It just cuts off at the period. It's like trying to understand a movie by watching 3-second clips in a random order.
It is, and there's an even deeper problem the paper points out, which I think is more important. A lot of these older algorithms treat that window as a bag of words.
A bag of words. That sounds really unscientific.
Oh, it's a literal term.
No way.
Yeah, they basically just dump the words into a pile and count them. They ignore grammar, they ignore syntax.
So wait, a sentence like, the dog bit the man and the man bit the dog.
To a bag of words algorithm, those look statistically identical. They have the exact same ingredients. But the meaning is completely different. In one, you need a bandage. In the other, you might need a psychiatrist.
Exactly. So they're missing the relationships. Even the more advanced graph-based methods back then, things using PageRank, often treated words like these little lonely islands. They didn't really get how the islands connected to form a whole continent.
Okay, so we have a computer with tunnel vision. It's ignoring grammar. It's looking at words in isolation. It's a mess. So enter the heroes of our story, Hugh and Lou. And they propose bringing in a sidekick to solve this. Coreference resolution.
Yes. This is the bridge.
For anyone listening who hasn't spent years in a linguistics lab, can you give us the clean definition? What is coreference resolution?
Sure. It's simply the task of figuring out which words in a text are referring to the same thing in the real world. The most common version is pronouns.
Okay.
So if I say, David is tired, he wants to sleep, coreference is the logic that connects he back to David.
Which, again, something humans do without even noticing.
We do.
Yeah.
But for a computer, David is just a string of characters, D-A-V-I-D. And he is a totally different string, H-E. It has no idea they're the same guy.
So the paper uses this perfect example to show why this matters for meaning. The manager example. I think this really makes it click.
Right. The three-sentence story. Sentence 1, the man is a manager.
Got it.
Sentence 2, he went to his office.
Tracking.
Sentence 3, he put the document on the desk.
Okay, now, if I'm that tunnel vision computer trying to understand the word put in that third sentence, he put the document. I mean, put is an incredibly vague word.
So vague. It could mean to place something, to express something.
Or a golf stroke.
Exactly. And if you only look at sentence 3, or the window around put, you don't have much to go on. He, document, desk. It's ambiguous.
But the researchers said, wait a minute. In sentence 1, the man is a manager. In sentence 2, he is the same as the man. In sentence 3, he is still the man.
Exactly. They're building a bridge. If the computer can use coreference resolution to link he in sentence 3 all the way back to manager in sentence 1, suddenly your context window isn't 5 words wide, it's the whole paragraph wide.
So it knows a manager is doing the putting. It's probably a professional action. It's not a golf putt.
It's borrowing context. It's breaking down the walls between the sentences.
So to do this, they used a tool called BART. I have to admit I saw this in the notes and laughed.
Yes, BART. Not the Simpson character. It stands for Beautiful Anaphora Resolution Toolkit.
Computer scientists and their acronyms.
Yeah.
Beautiful. Serious.
Oh, hey, if the code works, it's beautiful. It's a classic toolkit for tagging these relationships. They just use BART to draw these invisible lines between man, he, and his.
Okay, conceptually I get it, link words across sentences, but how do you actually build a system that does this? This is where the paper gets a bit technical, and I want to make sure we don't lose anyone. They talk about something called an IKN, an Instance Knowledge Network.
Right. This was actually based on their earlier work. Think of the IKN as like a 3-layer cake of understanding.
I like cake. Walk me through the layers.
So the bottom layer is the word level, just the raw words you see. The middle layer is the type synset level, which pulls from a huge database called WordNet that groups words by meaning. Synonyms, basically.
So it knows that car and automobile are in the same family.
Correct. That handles the dictionary part. And the top layer is the instance level, which tracks how a word is used in this specific text.
Okay, so they had this cake. What did they add for this paper?
They extended it. They called it the IKN, the Extended Instance Knowledge Network. And the secret sauce was structure. They didn't just want lists of words, they wanted a map. So they used the Stanford dependency parser.
That sounds heavy. Is that as complicated as it sounds?
It's a fancy name for something you probably did in school. It diagrams sentences. Remember drawing those lines? Subject connects to verb, verb connects to object.
Oh, vaguely. I think I tried to repress those memories. I remember a lot of chalk dust.
Well, the dependency parser does that. It creates a dependency graph. But the catch is, usually, those graphs stop at the end of the sentence.
Back to our isolated islands.
Exactly. The big innovation here was to stitch those graphs together using the coreference links. They created what they call a joint dependency graph.
A joint dependency graph. That sounds like a problem you'd go to a chiropractor for.
It's much more useful. Imagine the graph for sentence 1 and the graph for sentence 2 just floating separately. But because Bart told us that he in sentence 2 is the same as manager in sentence 1, we can draw a hard line connecting them.
So visually, instead of 3 separate spiderwebs, you have one giant web covering the whole paragraph.
That's it. And the paper describes this star-shaped connection where you have the prime base word like manager at the center and all the he's and his from the other sentences just radiating out from it.
That seems incredibly powerful. You're transforming the text from a string of pearls into a chain link fence. Everything is connected.
It is, and that connectivity allows for the real magic trick of this paper, transitive relations.
Okay, you're taking me back to high school math. Transitive property. If A equals B and B equals C.
Then A equals C.
How does that apply to words?
So let's say the computer has never seen the phrase, the manager put the document down. It has no record of that relationship.
Okay, so it's blind to that connection.
But maybe it has seen the manager went to the office, so it knows manager connects to office. And in other sentences, it saw he went to the office and he put the document down.
I see where you're going. It's like 6 degrees of Kevin Bacon for words.
It's exactly that, because he connects to office and manager connects to office, and he also connects to put. The system can infer a direct line from manager to put, even if they never appeared in the same sentence together in its training data.
So it's guessing they're related because they hang out with the same crowd.
Precisely. It's finding patterns that span across the whole narrative. It massively enlarges the context window without needing to process a million words at once. It just follows the threads.
This all sounds amazing in theory. Let's connect everything. But does it actually work? I mean, did they test it?
They did. They used the Sensible 3 all-words task.
Which is pretty much the Super Bowl for this specific niche of linguistics, right?
It is, and they trained it on the SemCore corpus. But what I liked about their strategy is they were very pragmatic. They didn't try to reinvent everything. They took the best algorithms of the time systems with names like Gamble, SenseLearner, and my personal favorite, R2D2.
I was hoping R2D2 would make an appearance. No lawsuit from Lucasfilm.
Apparently not. So they took these existing champions, and they basically said, let's see if our new system can give them a boost.
So they used a combined algorithm.
Right. They set up a kind of gatekeeper. They said, okay, first, we'll ask our new IKN system for the answer. If the system is highly confident, I think the probability score was above 0.8, they just take that answer.
They trust the web.
They trust the web. But if the confidence is low, they basically say, you know what? We're not sure. Let's fall back and ask Gamble what it thinks.
It's like having a really smart specialist on call. If the specialist says, I know this for a fact, you listen. If they kind of mumble and look at their shoes, you go back to the standard textbook.
That is a perfect analogy. And the results, they were striking. Every single combination performed better than the standard algorithm on its own.
Every single one.
Across the board. And here's a really interesting detail. The paper mentions that combining their tool with SenseLearner, which was actually one of the weaker algorithms by itself, sometimes produced better results than combining it with the stronger ones.
Wait, how does that work? You'd think strong plus strong equals strongest.
Not necessarily. It suggests that SenseLearner was making different kinds of mistakes. It had a different perspective. And because the EIKN system is looking at coreference, something SenseLearner totally ignores, they complemented each other perfectly.
So it's the value of diversity in problem solving. It's not just about raw power. It's about covering your blind spots.
It really is.
However, I have to play devil's advocate for a second. We have to talk about data quality, because when I read the limitations section, I had to pause.
The dirty data problem.
The paper straight up admits that the tool they used to build all these bridges, BART, the beautiful toolkit, wasn't perfect. It only had a precision of about 68%.
Which is okay, but not great.
Not great. That means almost a third of the time, it's linking key to the wrong person. Maybe it thinks he is the desk or the window.
Right.
So my question is, if your bridge is broken 30% of the time, shouldn't the whole system just collapse? I mean, there's that old saying, garbage in, garbage out. How do they get better results from such a flawed tool?
This is maybe the most counterintuitive finding of the whole paper. You would absolutely expect the noise to just drown out the signal. But the authors argue that the probabilistic nature of their training is what saves them.
How does probability fix bad data?
Well, the system isn't making a simple yes or no decision based on one single link. It's calculating these probabilities across thousands and thousands of sentences and patterns.
Okay, help me visualize that.
Think of it like taking a photo in really low light. If you take one picture, it's grainy, it's blurry, you can't see the details. That's your 68% precision.
Right.
But if you take 1,000 photos of the same subject and you digitally stack them, the random noise, the grain, it tends to be in different spots in every photo, so it cancels itself out. But the subject, the thing that's actually there, is in the same spot every time. It gets reinforced.
So the correct links like manager connecting to office happen so often and so consistently that they rise above the noise.
Exactly. The connection between manager and office creates a really strong signal, a high probability. But the wrong connections linking manager to a toaster or whatever random error Bert makes, those are random. They don't repeat often enough to cross that 0.8 confidence threshold.
That's fascinating. So the system literally absorbs the error.
It absorbs it. And that's a huge deal for developing AI. It means you don't actually need perfect tools to make progress. You just need robust systems that can handle a bit of imperfection.
It feels like a very human lesson, actually. We function pretty well, even though we mishear things half the time.
We do. We use context to fill in the gaps.
So, zooming out then, what's the big takeaway? We started this with a computer staring at just 5 words, totally confused about whether a bear was an animal or a market trend.
And we ended with a system that sees the whole continent. By integrating core reference resolution, by tracking the who and the what across sentences, we essentially gave the computer a memory.
It's the difference between just reading words and actually reading a narrative.
That's the goal. It really validates this idea that natural language understanding is an integrated process. You can't just separate the dictionary part of the brain from the storytelling part. They need each other.
And the authors hint at something in the conclusion that I want to leave everyone with, this idea of a feedback loop.
Yes, the iterative process.
Right, because if knowing the coreference helps us define the words, then shouldn't knowing the words more quickly help us get better at coreference?
It absolutely should. If I know for sure that bank means river, I'm much less likely to link it to the CEO in the next sentence.
So you can imagine a future system that just spirals upward. Iteration 1, better pronouns. Iteration 2, better definitions because of those pronouns. Iteration 3, even better pronouns because of the better definitions.
A virtuous cycle of understanding.
And that's the thought for the day. We spend so much time building all these separate specialized AI modules. But maybe the real breakthrough isn't in making each individual module smarter. Maybe it's just in letting them talk to each other.
I think that is exactly where the field is heading.
Thanks for taking this deep dive with us today.
Always a pleasure.